All right. Let's see. There. That one. Yeah, this problem here. So yeah, I did it a bit of piecewise here. So if k is 0, 1, or 2, then you have p q to the x. But if it equals m, which is 3 in this case, it's q to the 3. And that works out as you would expect it to, with a 50% probability of the 0, a 25% probability of the 1, and then a 1/8. Or no, yeah, a 1/8 on 2 and 3.
Okay, Matthew, Justin, Glauco, do you agree with this?
I did the same solution, only instead of Q, I wrote 1 minus P.
Yeah,
Okay.
I did the same thing as Glauco.
Okay. Well, by the way we determine mathematical truth, of course, is by voting. And it seems that this one is correct by vote. So go on, Adam, to the next part.
There we go. So in the next part, you simply replace the 3's with the general m. And in the first part, you run it up to m minus 1. And then in the second part, you just go to m.
Okay. Let's vote on this one. How many think that this one's right? It's a majority again. Okay, well, this is how we determine mathematical truth. Okay, anybody want to make a comment? Go ahead, Theo.
Wouldn't this assume that the probability of our stream having 0 and 1 is it's balanced between the two of them? Like the stream is not biased to have more 1s than 0s?
It'd just be like assuming that each like bit of the string is like independent of each other. So the probability of a 1 or 0 for each one would be you can just say like for a string of 0, 1, it's the probability of a 0 and a 1.
Mm-hmm.
So it's the probability of a success and a failure, I think. So it still lines up with the Bernoulli trials.
I do. Sorry. I do find something that concerns me with this solution is that when you add them all, you don't get 1. There is some probability missing there. So I was concerned
I added
with
them
that.
and got 1. For A, you add up and you get 1 for sure.
Do you think so?
I did the math on my calculator and I got a 1.
Okay. Maybe I had it bad wrong. Yeah. Okay.
Okay, Adam, thank you. Go ahead and unshare your screen if you will. Okay, so we had this one. Now I forgot what the other one was. What was the next one? Could somebody just tell me so I don't have to open
105. 2.105.
Oh, 105 right next to it. Okay.
Yeah.
Yeah, this, by the way, the Poisson distribution. Well, I guess this is not Poisson; it's geometric. So, yeah, here we have a decay with a probability of 1/2. Okay, I think this is pretty straightforward. Would anybody like to see this worked? Now, if you want to see it worked, I won't call on you. But did anybody like to see this worked? Okay, so everybody's happy with this one. What's the next one then? 313. This is the one we had a controversy on, right? Okay,
Mm-hmm.
we'll save this to next time. And then the next one was what?
426.
426.
Okay. There's one word that describes the answer. Anybody give me that word?
Interval.
No. Nice try.
Ugly?
Yeah, no, it's not ugly. This has a nice closed form solution.
I just think integration in general is ugly.
Well, yeah, but are you guys familiar with a tool that makes life easy for you?
Wolfram Alpha.
Wolfram Alpha. Did you work at Wolfram Alpha, Glauco?
Yes, yes, I did.
Okay, I want you to show these people Wolfram Alpha and show them how you did it, okay?
Okay, I cannot share a screen yet.
Yes, you can.
Okay, yeah, now I can.
Yeah, go not Wolfram Alpha, but the Wolfram Integral.
Oh, sorry.
Not Mathematica, but you have to go to a web page.
Then I share my work. Okay. Where is it?
Now, I'd like you to put up a browser and go to the Wolfram Integral, which is accessible to everybody.
Oh, okay. Okay, I'm going to the browser. Perfect.
No. No, you want, oh, there you go. Okay. Yeah, Wolfram Integral.
So to write integrate alpha divide.
Guys, I want you to know this because when I was a boy, you had to go to these very thick books by Abramowitz and Stegun or Gradstein and Rijek and spend a few hours leafing through the equations to see if you could find the right equation. And you can't, and that was really rough. But now we have this capability, and it's what?
No problem, because we have at Baylor we have free license for Mathematica. So in Wolfram Mathematica.
Okay, do it in
just,
Mathematica. Yeah, Wolfram Alpha is Mathematica.
Yeah, but if you want it to work like Wolfram Alpha, you have to write one equal, only one.
Okay, go ahead. Go ahead and do it in Mathematica then.
So you write one equal, and it works like Wolfram Alpha.
Now, see, the thing is that this used to be a integral everybody memorized, or you used to memorize the derivative, at least. Yeah, it's the arctangent. So the integral of that is an arctangent, which is a strictly increasing function. There's a bunch of parameters there which simply bias the arctangent, so it's non-negative all the time and goes from 0 to 1. So that's the answer there. And I think that you all know that, I hope you know and remember from calculus, the derivative of the arctangent is kind of that 1 over x squared plus a squared sort of form. So that's what it turns out to be. Okay?
Okay.
Okay, let's get back to the lecture then. And I still want to see if anybody does that. Did anybody do this conversion and they feel really, really happy about it?
I got the result from Wolfram Alpha, and then I tried to track it back, but I don't have.
Okay.
I wouldn't share it, I don't think.
This is supposed to be an easy, straightforward problem. Clearly, I did not do very well in tracking that. Okay, we were talking about information theory. So we're going to go now to the lecture and talk about information theory. And let's see, I want to go up here a little bit and talk about information theory. And I think we ended with this idea, the entropy of a geometric random variable. And we said that was HP over P, where H sub P was the entropy due to a Bernoulli trial. Here's one thing that's interesting about entropy. Entropy doesn't care about location. It only has to do with probability. It doesn't care where that probability is at. The probability only has to be there. So on the top, we have 4 equally spaced probabilities, uniformly distributed. That has an entropy of 2. On the bottom, we have some we have some other probabilities, but these probabilities are not arranged in a fashion which is easily accessed. But it turns out the entropy of that is also 2, because the only thing we care about is probabilities. We don't care where those probabilities occur. So this is an interesting phenomenon about entropy. We'll now deal with relative entropy. Relative entropy compares 2 probability distribution functions. One is P, the other one is Q. They both have the same number of elements from P1 to Pk. And so this is, in a way, looking at the entropy of P and Q. And this is the definition of the entropy between P and Q. It is recognized as the summation of, well, it's this cross entropy minus HP, but the bottom formula really is what captures it. It's minus the summation of P sub k times the log of the ratio between Q sub k and P sub k. What happens if P is equal to K, or I'm sorry, P is equal to Q? What does this summation become?
Wouldn't you be adding up a whole bunch of zeros if P
Would be
equals
adding
to-
a bunch of zeros. So therefore, this relative entropy becomes 0 when P is equal to Q. Good job. Yep, exactly. One of the things about the relative entropy is that it is always non-negative, and you do have a quality on this inequality only if P is equal to Q. And this can be proven. This is a quick proof. I don't want to belabor it, but the log of x is greater than 1 minus x. Bet you didn't know that. But this is a nice inequality that we can apply to the definition of the relative entropy. And we do this, and we get this expression. And then we break up the, well, we start with we apply the inequality here. So this is greater than or equal to 1 minus q over p to the x. But this is the summation over all of these probability mass functions minus the probability of all of these mass functions. And both of those equate to 1, right? You add up all of the probabilities and they all add up to 1. So this difference is equal to 0. So because of this, the relative entropy is greater than or equal to 0. So we've kind of shown this. Now, we can use this to show a very important property in that the maximum entropy that you can get out of capital K probabilities is a uniform probability. And so we know if we have K equally probable events from, say, 1 to K, we have all of these values here. Each one of the values must have a value of 1 over K. Each one of the values must have a value of 1 over K. So therefore, that's what this probability is. The probability is equal to 1 over K for the uniform probability. And we know that this is greater than 0. Now, if we parse this up, this is equal to the summation over K of P sub K times the log of K. And then what we're breaking it up as is the difference of the two sums. And this is minus the sum of the PKs times the log of 1 over K. This first entry is recognized as minus the entropy of the stochastic process of P sub K. And the second one, well, let's look at this. This log of 1 over K, that can go outside, can it? Because that's not a function of little k anymore. And so we have this is minus the log of K. And then we have the summation of K over P sub K. Well, the summation over all of these probability mass functions is 1, right? And so we find out then, this is the log of 1 over K. So we reciprocate that and make this into a positive log. And we get the fact that since this is greater than or equal to 0, we've proven that it's always greater than 0. We have just proven that all entropy is less than or equal to log base 2 of K. So this is interesting. If you have probability masses and you want to get the maximum average information, you make them all equally probable. Now here we see a relationship between Shannon entropy, and this is Shannon entropy, and the entropy of that we get in thermodynamics. When we say that gas in a room is at maximum entropy, what does it mean? It means it's uniform. The distribution of all of the velocities of every point in the room is uniform, exactly the same thing, right? And there is a relationship between Shannon entropy, as we've defined it here, and thermodynamic entropy. If you take the course in information theory, you'll be able to find it. Or you'll be able to understand that. We'll go into that a little bit more. Let's return to the balls problem and probability of solutions. Suppose we have 16 balls in an urn. I have no idea why they always place the balls in an urn, but we have 16 balls. 4 of the balls have a number 1 on them. 4 of the balls have number 2. You can see there are 2 balls with number 3, 2 balls with number 4, and 1 each of 5, 6, 7, and 8. So you place it in an urn, you juggle it, and then you reach in and you choose one. So the probability of any one of these coming out is equal to 1 over 16. But that's not the problem we're going to look at. We're going to look at the fact that somebody has chosen one of these balls, and you want to go back to this idea of yes and no questions and figure out the minimum number of questions that you have to ask in order to uniquely identify the ball. Here's one technique that, first of all, sounds like it might be good. We choose up here, we choose the ball which has the most. So we say, is it ball number 1? Well, if it is, we're done. So you have one quarter of a chance of getting this right, correct? If it's no, you say, well, is it ball number 2? And if that's right, you get it right. It costs you 2 questions to get the answer, but you got it right in 2 answers. And so you begin to work down the chain as you get into smaller and smaller probabilities. You ask, is it number 3? Is it number 4? Is it number 5, etc., all the way down here. Now to get to the 8, it's going to cost you like seven questions, 7 yes or no questions. So we're going to look at the expected number of questions. How many questions do you have to ask? Well, a quarter of the time, you get it right in 1 try. That's what this is, right? Also, on a quarter of the time, you get it right on 2 questions, right? So a quarter of the time, you get it answered in 2 questions. An eighth of the time, you're going to get it answered in 3 questions. It's an eighth because yes, is this purple ball, and this purple ball only has a probability of 1 out of 8, 2 out of 16, or 1 out of 8. In a similar fashion, the next balls, which are the 4s, that's gonna cost you 4 questions, and that's only a probability of 1/8. And then you go to the individual cases. It's going to cost you 5, then 6, then 7, and then the last case is 7 questions. One of the answers gets you this way, one of the answers gets you this way. So we have both the 7 and the 8 being 1/16, and it costs you 7 questions. So this is the expected value of the number of questions that you have to ask. If you add them up, you get 51 over 16, okay? Now, it turns out that this is not the best way to query and find out for 20 questions what the ball is. A better way is the one illustrated on the next slide. You remember interval halving? where we took those 16 squares and we said, is it above or below something? We can apply that and generalize this to the ball problem. We're going to take the ball and we're going to take these values and we're going to divide them into equally probable events. Now, what is equally probable? Well, first of all, this is equally probable, right? That is, the probability that it's above the line is exactly the same as it is below the line. So this is kind of like interval halving. So the first thing we ask is x less than or equal to 2. That would correspond to these two lines, right? And if x is less than 2, then we can find out whether it's a red or a green ball in only one more question, right? Is it red? Is x equal to 1? Yes. If it's no, we know that it's green. Now, if this first case is the answer is no, we know that it's neither the 1 or the 2. So we go to the second question, and then we said, is x less than or equal to 4? Notice it's dividing this again, right? It's dividing it into equal partition. And then you say, is x equal to 3? And yes or no. So it takes, in order to get here, it takes us 1, 2, 3 questions. And we keep on doing that. We keep on dividing it into portions. Say, for example, it's in this other square, then we know it's a 4, a 7, or a 8, and we keep on doing this until we reach the final solution. So the longer paths have smaller probabilities. That's what we want to do. If you have a small probability of coming out, then you want to take a longer path to get there. And the high probabilities you want to knock out of the way with your first guesses. So let's look at this problem. What's the chance that you get it on 2 questions? The chance you get it on 2 questions, well, you get the 1 on 2 questions. That has a probability of 4th. And you get the green on 2 questions. That has a probability of a 4th. So therefore, you have a 50-50 chance of finding out what the ball is with 2 guesses. If not, you go to the second tier. And here you're going to have 3 questions, because you have to get a no to your first question and then a yes to your second question as you interval half, and then a yes or a no to your final question. So for the purple and the brown balls, that's an 1/8, because that's 3 questions, 1/2, 1/2 times 1/2 times 1/2. And then it's going to take you 3 queries. And we keep on going down the line. For 16, it'll take you 4 queries. Probability of 16th, it'll take you 4 queries. A probability of 16, it'll take you 4 queries. And a probability of 16th, it'll take you 4 queries. And that turns out, if you add them all up, to be equal to 2.75 bits. So the number of questions that you have to ask on the average in order to get this solution would be 2.75. That would be the average number of questions that you would have to ask. And you could literally choose different balls. Remember Monte Carlo simulation? You could use different balls and go through this decision tree 1 billion times, and you would find out the average number of questions that you would ask is going to be equal to 2.75. Okay? That makes sense, and that's very interesting. But let's do something else. Let's go back and look at the entropy of this. We have a probability here of equal to a 4th. We have the probability here equal to a 4th. We have the probability that it's being a 3 is equal to an 1/8, etc. Probability of 4 is an 1/8. And then each one of these has a probability of 1/16. So these are piece of K's. So we can do 1/4 times the log of 1/4 plus 1/4 times the log of 1/4 plus 1/8 times the log of 2/16, etc. So this is what we're doing now. And we're going to compute the average of the entropy of this corresponding distribution of balls. And guess what it turns out to be? 2.75 bits. That's incredible. I think it's incredible. Probably not obvious at first, but notice on the previous slide, that's how many questions you had to ask. That was a total. That was a total entropy, or the total number of questions that you had to ask, and the total number of questions you have to ask is exactly the same as the entropy. So this gives you another interpretation of the entropy and how powerful it is. It turns out that if you optimize it, you will always equal or exceed the entropy. You will exactly get to the entropy if all of your probabilities are a power of 1/2. And that was the example that we had in the previous case. All of the probabilities were powers of 1/2. If they're not powers of 1/2 and you're using interval division, then the number of queries that you have is going to be a little bit greater than the entropy. In fact, we can show that the number of questions independent of the probabilities, the number of questions that you ask always lies between the entropy and the entropy plus 1. We're not going to show that here, but that's an interesting result that comes out of this. So you can see the power of entropy in describing phenomenon. And we've just limited what we're doing, by the way, to what we're doing. We're limiting what we're doing to just probabilistic insights, if you will. There is a lemma that if there are k solutions and the length of the path to the kth solution is lk, then L sub k, then this summation applies. Boy, that's not obvious at all, is it? Well, let's go back to here. What is the number of queries here? The number of queries here is 2. The number of queries here is 2. The number of queries here is what? 3? Is that right? 1, 2, 3. Number of queries here is 3. The number of queries here is, let's see, 1, 2, 3, 4. So the number of queries for this one is 4, 4, and over here is 1 question, 2 questions, 3 questions, 4 questions. Wait, did I do something wrong? 1, 2, wait, 1, 2, 3, 4. No, that's right. 1, 2, wait, 1, 2, 3, 4. Yeah, I guess it's still 4, isn't it? Okay. Did I do something wrong here? 1, 2, 3, 4. It takes 4 questions. 1, 2, 3, 4. I guess it does. Well, I don't like this because it isn't going to allow me to get the results that I want to get. These are the lengths of the trees. This takes 2 steps. And so what we're saying then is the following, is 2, if I did this right, 2 to the minus 2 plus 2 to the minus 2 plus, no, this works out, okay, plus 2 to the minus 3 plus 2 to the minus 3. See what I'm doing? I'm taking the path lengths, and that's to the minus L problem. Plus 2 to the minus 4 plus 2 to the minus 4 plus 2 to the minus 4 plus 2 to the minus 4. That should add up to 1. I took each of the path lengths and raised 2 to the power of minus the number of questions that I would have to ask. And that's the path length. And that is all equal to 1. So notice this is just to show you, this is what? A fourth plus a fourth. Man, I hope this works out. Plus an eighth, plus an eighth. I'm doing this series here. Plus a 16th. But there's 4 of those. And that should equal to 1. And it does. If you do the math, if you do the arithmetic quickly in your head, you see that it does add up to 1. Isn't that interesting? The answer is yes, it is interesting. So we go to this final thing, which tells us that the summation of 2 raised to all of the path lengths to get to a solution must always be equal to 1. This includes optimal and non-optimal trees, if you will. Okay, we've gone through that, gone through that, gone through that. And so, whoops, I'm going backwards. That's the reason these things look familiar. Shoot. Okay. Hitting the wrong keys. So this is something which is always true. This is what we just illustrated. And if you use this inequality and look at the path lengths and look at the relative entropy, the expected value of number of the questions minus the entropy is equal to some math here. And this math shows that the expected number of questions minus the entropy is always non-negative. So therefore, the number of questions must always exceed, on the average, must always exceed the total entropy. So this is a very interesting foray into applications of probability into information theory. And I thought it would be fun to go down this path to give you an idea of how probability is applicable to information theory. If it whets your appetite and you want more, then take the course in Introduction to Information Theory, which is a graduate course here at Baylor. Okay, we have about 15 minutes left. Are there any questions on the entropy lecture then so far? Okay, crickets. Next thing we want to do is look at functions of a random variable. This is this is a very interesting topic and very applicable. And let me give you an example of a function on a random variable. Say you have theta. You're measuring an angle, and it lies between 0 and 2 pi. So you know that the distribution of theta, if you look at the probability distribution function and it's uniform, the angle chosen randomly will be between 0 and 2 pi. It'll have a height of 1 over 2 pi. Why? Because the total area under this rectangle has to be equal to 1, right? So this would be f of big theta of theta versus theta. So we know that this is a uniform random variable. We know the distribution. We can talk about probabilistically the random variable. But what if you let something like x equal to the cosine of theta? So I'm using capital letters now to denote random variables. So theta is the random variable. You spin a wheel of fortune, it points to an angle between 0 and 2 pi, and you know that that's uniform, and then you want to take the cosine of it. Why do you want to take the cosine of it? Well, on the real plane, if you have a complex number and you want to find the complex number of length 1, and you want to find the real part of it, you take the cosine of theta of that random variable, right? So the question is, what does the random variable f sub x look like? That's the sort of question that we want to answer here. And I'm going to give you, first of all, a solution, and this solution will mean nothing to you because it looks like mathematical gobbledygook, but we will unpack it as we go on. And this is as follows. If you have y is equal to g of x, in other words, you're given a distribution function for x, So you know what the random variable x is. And you make a random variable transformation. Y is equal to g of x. So g of x could be any function. It could be the cosine, the sine, the tangent. It could be the squaring value. It could be any function that you want to. The question is, what is the distribution of y when you do that? And the way you do it is solve the roots of x, and y is equal to g of x, call the roots this, and then this is the transformation. Again, that probably looks like gobbledygook to you. That's okay. We'll unpack it and we'll get back to it pretty soon though. Okay? Let's run before we can walk. Here is a special case where y is equal to g of x is strictly increasing. So therefore, you have y and a transformation on a random variable, and this transformation on a random variable is strictly increasing. Now, if it's strictly increasing, if a is less than b, which we see down here, if a is less than b, then it turns out g sub a is going to be less than g sub b, right? And this is kind of cool because it allows us to maintain inequalities. So with that, let's begin to look at a transformation on a random variable when it's strictly increasing. Now, here is something interesting. If y is equal to g of x is strictly increasing, so is its inverse. Think, for example, of y is equal to e to the x. E to the x we know is strictly increasing, right? If we solve for x, we get the inverse. This is g of x equal to y is equal to e to the x. X is equal to g inverse of y, which in the case of y is equal to g of x, we know it's the logarithm, right? The natural logarithm. And the natural logarithm looks like this. It is also strictly increasing. You will notice that if we take e to the y and think of this as a curve, and we flip it, that we get this. This is nothing more than an e to the x curve. If we have y and x here, we can think of this curve as the log of y. Or if we look at it sideways and look at x, we see that it's e to the x. Notice these curves have exactly the same form, except they're kind of flipped on each other, aren't they? Right? So inverses are flipped versions of the original. So if we have a y is equal to g of x here, which is strictly increasing, then the inverse is exactly the same curve flipped around so that instead of the y-axis going up and down, the y-axis goes from right to left. And instead of the x-axis going from right to left, the x-axis goes up and down. So they're exactly the same functional plot. Well, here we go. This is actually pretty easy. We want to find, don't forget what we have. We have the outcome x, and we know what the distribution is. We want to find the distribution of y is equal to g of x. Again, y corresponds to a random variable. And we go back to the fundamentals. We go to the distribution of y. That's equal to the probability that y is less than or equal to x. This is by definition. So there's some mathematicians that like to put a little colon before the equal sign to mean it's equal to this by definition, right? But this is the same as the probability that g of x is less than or equal to y, because y is equal to g of x, right? Now here's where the inversion comes in. We've assumed that g and its inverse are strictly increasing. So what's cool about this is we can operate on both sides by g inverse and maintain the inequality, can't we? I mean, if we have, for example, if we have something like a is less than or equal to b, since e to the x is strictly increasing, we can assure ourselves that e to the a is also going to be less than e to the b, right? as long as we operate on both sides by a strictly increasing function. And what happens if you apply a G inverse to the original function? Well, you get the original thing back, right? You get the original random variable back. The log of e to the x is equal to x, right? Or e to the log of x is equal to x. So we get back exactly the same function. We're inverting the function. And this is less than or equal to g of x and y. Well, you remember that f sub x is equal to the probability that the random variable is x is less than or equal to x, right? That's the definition of the cumulative distribution function for x. So we are really nice here because we have the probability that x is less than or equal to this g inverse of y, which takes the place of our x. And so the answer is that the transformation on the random variable is that the new cumulative distribution function is equal to the old cumulative distribution function, except instead of being evaluated at y, it's evaluated at g inverse of y. So that is the transformation that we like. And again, g of x has to be strictly increasing here. So this is the solution from the last slide. The distribution for y must be equal to the distribution of x except evaluated at g inverse of y. Many times we don't want that. Rather, what we want is the probability density function, which is the derivative of the cumulative distribution function. So we would like to differentiate this. So we differentiate this f sub x of g inverse of y. And well, what is that? It's the inverse, it's the derivative of f sub x times g inverse of y. And this is where we go back to the chain rule of calculus, calculus 101. And we know that this, the derivative of this, is equal to the derivative of the argument times the derivative of this evaluated at g inverse of y. So this is the formula if we want to go, if we have a y is equal to g of x, and we know that g of x, we know that g of x is strictly increasing, right? Has to be strictly increasing. That we can get the distribution of y from the distribution of x by this formula. So this is all well and good. Now, here's something interesting. I'm going to see if I have sufficient bandwidth to pin myself and to share my video. Tell me if I'm still breaking up. Am I still breaking up or am I doing okay? Thumbs up, thumbs
fine as well.
Okay, so far so good. Okay, here's what I want to do. I want to get a paper towel here. This is my paper towel. And I'm going to write on the paper towel. Let's hope this works. Well, wouldn't you know, my pen isn't working. I'm having one of those days, guys. My pen that I had in preparation for this is not working the way that it should. So let me try this. Well, that isn't working. I'm having a bad hair day, man. Okay, well, I'll try to get this to work. Let's see if I can coerce this. And now I've lost my original pen. Okay, we'll just try it and see what happens. Okay, here we have, can you see this? Can you see y is equal to g of x, okay? So this is kind of cool. Now, if you turn this paper around, you can still see the ink bleeding through the other side, right? You can't see it very good. I'm gonna draw over it though. So I've simply traced over some of the stuff that has gone through. Okay. So this is g of x, and let's see if I have this right. Nope. Oh, I got to do it this way. Okay. Okay, this is equal to g of x, right? And this is equal to g inverse. Notice that now my x-axis is y. So if this is e to the x, then this is kind of a logarithm. It's the inverse. Kind of interesting, right? So that's the way you get logarithm from e to the x. Now, follow me now. If we do the derivative here, we all know that the derivative is rise over run, right? So I've drawn a little triangle here of rise over run. Now let's look at it from the other side. Let's look at it from this side. Now the rise becomes the run, and the run becomes the rise. I'll redraw the triangle here so you can see it. Right? Now the rise becomes the run, and the run becomes the rise. And over here, we do have the normal rise over run, but here we have run over rise. So what does that tell you about the derivatives at a point? The derivative of this point is equal to 1 over the derivative at this point. So the derivative of a function at a point is equal to 1 over the derivative of its inverse at that point. Thus ends my high-tech use of paper towels to explain derivatives. So with that, let's go back to to what we were talking about. I'm going to stop my video. This is what I was trying to talk about here. This is just what I showed you on the paper towel, that the derivative of the inverse is equal to 1 over the derivative of the original function. Do you see that? So that's what I illustrated with the paper towels. So if we go back, here, we see that we have the derivative of the inverse. So we can actually look at the derivative of the inverse as 1 over the derivative of the original function. So that's the point here. So for this reason, and by the way, notice that this is nothing more than x, right? Because x is equal to g inverse of y. And this, we said, is 1 over the derivative on the other way, in the other way of looking at it. So here's what it boils down to. We can write this original result as f sub y of y. This, again, is the transformation of y is equal to g of x. This can be written as f sub x of y. Don't forget x is equal to g inverse of y. Yeah, right here it is. X is equal to g inverse of y divided by the derivative, since the derivatives reciprocate between the function and the derivative. This is only applicable for a strictly increasing function. Only applicable for a strictly increasing function. We could go through the same result using a strictly decreasing function. And if we used a strictly decreasing function where we had the inequalities, we'd have to flip the inequality around. And it turns out that if we had a strictly increasing or a strictly decreasing function, then we could we could generalize this formula by, in the denominator, putting the magnitude of the derivative of the function. The y is equal to g of x. So this is a nice general formula if you have a strictly increasing or a strictly decreasing function. Any questions on this at all? Okay, my homework is to work out the earth problem, and I'll be probably giving you some homework on information theory. So stay tuned to the spreadsheet that we talk about. Any questions at all?
Did you still want us to look out 3.13?
Yeah, let's save. I'll put that on the agenda for next time. Okay, since it looks like I screwed up. Okay, hearing nothing else, go ahead and put the stuff in box. If you want to change what you've done, you're welcome to do that, and go ahead and stick it in box. If you had any problems using box at all? No? Okay, good. Okay, thank you, gentle people. We will see you on the flip-flop. Bye-bye.
Adios.
Hi, Glauco.
Hi.
You know
I'm
what?
just leaving. Yeah.
Hold on a second. I don't know what's wrong with I can't get my Zoom to run up. Glauco, I'm having a terrible day. Oh, I know what it is. Okay, I got it going now.